Time to take a look at another concept. This one comes out of chapter 14. It is the activation energy from the Arrhenius equation. And this is one, where, calculate the value of the activation energy. And there's a couple of different types of problems here. One of them will give you several rate constants and temperatures and ask you to do the plot and do the graph method for determining activation energy. Otherwise, they will give you what is sometimes referred to as the two-point form of the Arrhenius equation. And that's the one we're going to take a look at here. This is the one where, we in chemistry sort of say, oh, look, here are 2 points. My gosh, they draw a straight line. Let's draw conclusions from that. Yeah, it's a bit of an oversimplification, but it's a common type of question in end of chapter stuff, usually in the kinetics chapter. So let's take a quick look at the equation itself and then the question that we're going to go ahead and try to answer. So here it is, the two-point form of the Arrhenius equation. Most students, when they encounter that thing, go, ooh, and there are a lot of moving pieces in here, but really it is basically just a classic plug-and-chug algebra problem. You do have to read the problem carefully, though, to make sure you understand what component this thing is asking for and which one of the components are actually given in the problem and which ones might need a little modification. So, without further ado, here is the text of the problem itself. And clearly they're asking for, here are 2 rate constants at 2 different temperatures. What is the value of the activation energy? And so that's the thing we're after. Now, it is kind of buried in that equation, so we are going to have to apply some algebra. Now, at a lesser university, students get all quivery about this sort of thing, but here at the Harvard of the South, we look at that and say, my God, we were doing that back in 3rd grade. And so, yes, we do have to isolate the activation energy, and it's really not too bad. You have to move the temperature terms to the other side by dividing it on both sides, and also move the gas constant, the R, to the other side by multiplying it on both sides. So when you're all said and done, you're going to have something that'll look like this, R, natural log K1 over K2. I'm going to put those in parentheses, over 2 minus 1 over T1. Okay? And there it is in its glorious worked out form. And now we start taking an inventory of the pieces that the problem actually gives us. And they tell us that this reaction that we're trying to study has 2 rate constants, okay, called K1 and K2. And they give us the values, and 0.0796, and reciprocal moles per liter, reciprocal seconds. And they tell us that the other one, 0.0815, reciprocal moles per liter, reciprocal seconds. Now, they tell us right in the problem that these are second order rate constants. Who cares? This Arrhenius equation works for any type of reaction. First order, second order, 0 order, does not matter. So that's a bit of extraneous information here. But we have our 2 rate constants. We have that part taken care of. And they also very specifically tell us that this rate constant, K1, was measured at a certain temperature. And we're going to call that T1, because you must keep the rate constant and the temperature tied together. If this is the rate constant at one temperature, then that temperature must also be called K1 and T1. The temperature that they measured here is at 737. And they give us degrees C. Then they jacked up the temperature to 947. Not easy experiments to do at those types of temperatures. And measured the second rate constant. I wrote K1. Oh, that's embarrassing. Oh, well, now it's K2. We must, again, have your, the temperature and the rate constants, K1, T1. This temperature and that rate constant, K2, T2. Okay? And now we have the temperature components. The only thing we're lacking is the gas constant itself, and it's a constant. You look that thing up. Now, remember, like a lot of constants, it has a lot of different values depending upon the units. For an activation energy calculation, the most common units are these, the energy units, 8.314 joules per mole Kelvin. And now we're almost ready to start plugging and chugging, but being careful, diligent students, we are going to notice a potential issue coming up. Our units of the units of the gas constant here, joules per mole Kelvin, they handed us temperatures in degrees Celsius. We start having memories, perhaps not fond ones, of all the gas law chapters where we had kelvins and temperatures, and every once in a while they even throw Fahrenheit in there just to make life interesting. Yes, indeed. We cannot use temperatures in degrees C or in Fahrenheit or in any other unit. They must be in Kelvin. Luckily, it's a simple sort of thing, plus 273.15. And so we're going to just simply convert those into Kelvin. And I wrote them down over here, 1010 Kelvin and 1220 Kelvin. And those are the temperatures that we have to use in order to solve this thing. Now, reading through the problem, we carefully write down the information they give us, and we realize we now have all the components necessary to make this thing work. So now it's a plug and chug problem. So away we go. Activation energy, okay, is 8.314 joules per mole Kelvin times the natural log of K1 on top 0.0796 over 0.0815. Okay, I'll close those parentheses as well. All over. Oh man, there's just so much stuff going around in here. Now, the first one is T2, 1 over T2. I have to make sure I get that straight. 1 over 1220 Kelvin minus 1 over 1010 Kelvin. Okay, there's all the pieces. Before we start calculating, always a good idea to make sure units are going to work out properly. It's always a good idea to check this. In the logarithm term, we have matching units top and bottom. They are going to cancel because they're divided, and then within the logarithm term, but that looks nice. Over here, we have joules per mole Kelvin. We have kelvins up here. We have kelvins down here. Those will cancel, leaving me with joules per mole, which is a common activation energy unit, either joules or kilojoules per mole. And so now we are ready to go. Do be able to do this type of calculation. A lot of times, this is a fairly sophisticated one on your calculator. If you just haul out the little TI calculator or whatever it might be, it does take a little bit of doing to make sure you get it right. But hauling out the calculator and doing the magic calculator dance gives me 1,150 joules per mole. Okay? Now, that seems like a large number. It is a large number, but actually more typically you'll see these things in kilojoules per mole. That's 1.15 kilojoules per mole. Okay, so there it is. A worked out example of the two-point form of the Arrhenius equation. It's a scary looking equation, but it's just basically an algebra problem, how to solve for the one variable you need. Make sure you list all the information that the problem gives you. Units do have to match up, and then it's just a classic plug and chug. So give that a try. Hope it helps, and talk to you later.